Hello, welcome back. In this video, we'll discuss the photoelectric effect. In 1857, Hertz discovered that electrons are ejected when ultraviolet light is incident on zinc metal plates. Later, similar experiments were conducted using alkali metals and similar results were also found. The phenomena of ejection of electrons from the metal surfaces is known as photoelectric effect, and the electrons thus ejected are known as photoelectrons. The current due to these electrons in the circuit is called photocurrent. Photoelectric effect is the phenomena in which electrons are knocked off a metal surface when light is incident on it. Photoelectric effect is the phenomena in which electrons are knocked off a metal surface when light is incident on it. The photoelectric effect was first observed in zinc plates and later in alkali metals such as lithium, sodium, potassium, etc. The metal that emits photoelectrons is said to be a photosensitive material, and the liberated electrons are called the photoelectrons. The metal that emits photoelectrons when light is shined is said to be photosensitive material, and the electrons are known as photoelectrons. So the metal surface that emits the electrons is known as the photosensitive material, and the electrons that are ejected from the metal surface are known as photoelectrons. The electronic emission increases with the intensity of the radiation falling on the metal surface, since more energy is available to release the electrons. Now we shall look at the experimental setup. This is the experimental setup. In this, we have either a quartz tube or a glass tube in which we have two electrodes, one cathode and one anode. There is a small window attached to the tube so that light can enter into the discharge tube. The entire tube is evacuated so that the electrons can freely move towards the anode. A potential difference is applied across the discharge tube, and we have an ammeter here and a voltmeter. The cathode is made using a photosensitive material, could be an alkali metal. When light is made to shine on the metal surface, it starts emitting the electrons, and these electrons would move towards the anode since it is positive with respect to the cathode. So these electrons, they establish a current in the circuit. The current can be measured using the ammeter. Current, we call it as the photocurrent. The number of electrons that are emitted from the cathode and the kinetic energy of the electrons depends on various factors. The factors are the number of photoelectrons emitted and their kinetic energy depends on the potential difference between the cathode and the anode. It depends on the intensity of the incident radiation. Further, it depends on the frequency of the radiation, frequency of the incident radiation, and it also depends on the photometal plates used for the anode and cathode. These are the factors that can influence the number of electrons emitted from the cathode and also the kinetic energy of the electrons. The factors are: they depend on the potential difference between the cathode and the anode. They depend on the intensity of the incident radiation. They depend on the frequency of the incident radiation and the metal plates that are used for the cathode and the anode. The electronic emission increases with the intensity of the incident radiation because more energy is available to release the electrons. But there exists a characteristic frequency. For each substance, there is a minimum frequency called nu0 of light. For light of frequency less than nu0, photoelectrons are not seen. For each photosensitive material, there exists a characteristic frequency represented with a nu0 of light, and for light of frequency less than nu0, that is the characteristic frequency, photoelectrons are not produced. However intense the incident light may be. The minimum frequency nu0 is called the threshold frequency, which means for light of frequency less than nu0, no photocurrent can be there in the circuit. or photoelectric effect cannot be seen. The maximum kinetic energy of the photoelectrons varies with the frequency of the incident radiation, and it is independent of the intensity of the light. In 1905, Albert Einstein successfully explained the photoelectric effect. In the Einstein's explanation, the incident light is treated as a stream of photons. The incident light is treated as a stream of photons. When it is treated as a stream of photons, if you have a monochromatic light, means the light which is having single color. In a monochromatic light, the energy of such monochromatic photons is given by h nu, where nu is the frequency of the monochromatic light and h is the Planck's constant. When these photons they encounter the electrons in the metal, they give up their energy to the electrons. However, the electrons are held within the metal by a potential barrier. So when photons interact with the electrons, they transfer energy to the electrons. This process of transfer of energy will leads to the liberation of the electrons in the metal piece. However, the electrons are held within the metal by a potential barrier at the surface. Therefore, in order to observe the photoelectric effect, an electron should have enough energy to overcome the potential barrier at the surface. Therefore, it requires an input energy that is equal to the work function W0. Photoelectric effect can be observed only when enough energy is transferred to the electrons to overcome the barrier, to overcome the potential barrier. This input energy is called as the work function. It is represented with a W0. So one can observe the photoelectric effect only when the incident photon's energy h nu is greater than or equal to W0. That is the favorable condition for the photoelectric effect to take place. Therefore, out of the incident energy h nu, a small portion W0 is spent on overcoming the potential barrier, and the balance energy h nu minus W0 is given to the electrons as kinetic energy. A small portion of the incident photon energy, that is h nu, is spent in overcoming the potential barrier, and the rest of the energy, that is h nu minus W0, will be the kinetic energy of the photoelectrons. So the kinetic energy of the photoelectrons is equal to h nu minus W0. Say this is 1. By applying the conservation of energy, one can write h nu is equal to W0 plus half mv max square, where m is the mass of the electrons and v max is the maximum velocity the electrons can possess when frequency of light nu is incident on the metal piece. This equation is known as Einstein's photoelectric equation. We call this 2. The Einstein's photoelectric equation explains all the features of the photoelectric effect. From this equation, it can be seen that a photoelectron is emitted from the metal only if the energy of the incident photon h nu is greater than or equal to W0. Because if the incident photon energy h nu is less than W0, then the electrons are not released from the metal surface. On the contrary, if the incident photon energy h nu is more than W0, then the electrons will be liberated and emitted from the metal surface with certain amount of kinetic energy. From the experimental results, if one plots the frequency of radiation along the x direction and the emitted electrons kinetic energy along the y direction, then we get a linear plot like this. The linearity of this plot indicates that the kinetic energy of the photoelectrons is dependent only on the frequency of the incident photons. When say h nu 0 is equal to W0, when the incident energy is equal to the work function, we are representing the frequency with nu 0. Then one can write nu 0 as W0 upon h. And this indicates that there exists a threshold frequency nu 0. Otherwise, it cannot be seen. This we call 3. The kinetic energy of the photoelectrons can be measured by subjecting them to a repelling electrostatic force. By giving a negative potential to the anode, one can establish a repelling electrostatic force within the discharge tube. The electrons ejected from the cathode are decelerated due to the negative potential. The kinetic energy of the photoelectrons can be measured by applying a negative potential to the anode. Because of this negative potential, the electrons ejected from the cathode are decelerated as they travel towards the anode. When the repelling force is made large enough, even the electrons with the highest kinetic energy are stopped from reaching the anode, and hence the current will drop to zero in the circuit. Please recollect that this is the experimental setup we have. In this, we are applying a negative potential to the anode so that the electrons ejected from the cathode, they will be decelerated. A range of kinetic energies are possible for the photoelectrons. So different electrons with different kinetic energies would propagate between the cathode and anode with different velocities. When we apply a negative potential here, the electrons will be decelerated, and if the negative potential is sufficient enough to stop electrons with maximum kinetic energy, then the current in the circuit is zero. Under such conditions, the potential that is applied is called as the stopping potential. The potential difference that stops the electrons from reaching the anode and reduces the current in the circuit to zero is called stopping potential. The stopping potential is represented with a Vs. Therefore, the kinetic energy of the electrons is given by EVs. We call this as 4. From the previous expressions 2, 3 and 4, one can write the stopping potential as h by E into nu minus nu 0, where nu 0 is the frequency corresponding to the work function. This relation shows that the stopping potential and hence the kinetic energy varies linearly with the frequency of the incident radiation. For different metals, if you plot along the y direction, stopping potential and the frequency of the incident radiation along the x direction, for each material you have a nu 0 here. We have a linear relationship between the Vs and the nu. Intercepts with the x-axis gives us the nu 0, and the slope of the curves is h upon E. So the relationship shows that the stopping potential and the kinetic energy varies linearly with the frequency of the incident light, and the emission of electrons is instantaneous. The photoelectric effect confirms the existence of energy in the form of discrete quantas. In this video, we have started our discussion by stating that photoelectric effect was discovered by Hy in 1857. The photoelectric effect is the phenomena in which electrons are knocked off a metal surface when light is incident on it. It was first observed in zinc plates. We have said that the metal that ejects the electrons when light is shined is said to be photosensitive material, and the electrons are known as the photoelectrons. We have seen the experimental setup. Current in the circuit we call as the photocurrent. We have seen the factors affecting the number of electrons emitted and the kinetic energy of the photoelectrons. They are the potential difference between the cathode and the anode. It depends on the intensity of the radiation, the frequency of the incident radiation, and the photometal plates used for cathode and anode. We have seen the explanation given by Albert Einstein for the photoelectric effect, in which the incident light is treated as a stream of photons. We have seen what is the work function. We have seen that a small portion of the incident photon energy h nu is spent in overcoming the potential barrier, and hence the rest of the energy h nu minus W0 will be the kinetic energy of the electrons. We have written kinetic energy as h nu minus W0, and this is written as h nu is equal to W0 plus half mv max square. This equation is called as Einstein's photoelectric equation. We have obtained a relation for nu 0 as nu 0 is equal to W0 upon h. We have seen that the kinetic energy of the photoelectrons has a linear dependence on the frequency of the incident radiation. We have seen what is stopping potential. We have said that the kinetic energy is equal to EVS. Under such conditions, the electrons will be stopped from reaching the anode, and we have shown that the stopping potential and the kinetic energy varies linearly with the frequency of the incident light. We have also said that the photoelectric effect confirms the existence of energy quanta. Thank you.